be talking about mathematical incompleteness today. I am conscious of the time. The first time I ran through this talk, it was an hour. So there's a balance between actually trying to do some of the maths, but also not take forever. So I'm sorry if that balance isn't quite right, and if it's maybe a bit hard to understand. And because of the timing, if you could save any questions for the end, that would be great. But please do ask questions, because it's a fascinating topic, and so I'm sure you'll have loads of questions to ask. So before delving into mathematical incompleteness, which is quite a complicated, no problem, complicated concept, we can just think about what is mathematics, first of all. And there are a whole load of sort of philosophies of mathematics, but again, time is an issue, so I'm just going to focus on one undeniable aspect of mathematics, which is that it is a natural ability that we have evolved through evolution, and because of that it's observed in other animals as well. So here we have three mathematicians. They may be the most attractive mathematicians we'll see on this slideshow, but yes. They're okay. The chicks need to work in teams, or else they can't. No, that's not true. So lionesses, 3-day-old chicks, and chimpanzees. And we have, it's much easier to test inequalities than equalities, because animals will tend to think about what's bigger, what's smaller. So they've been observed doing inequalities, and again, it is only what has been observed in experiments. For all we know, they could be doing n-dimensional calculus in their heads, but we have no way of observing that, so we may be underestimating their abilities. But so here are three inequalities. We're going to have a tiny bit of interactivity at the start, voting for which animal you think can do which. So 4 is greater than 1 is really basic. It's just one number is bigger or smaller than the other. 4 plus 5 is greater than 1 plus 7. You need to do some addition. And even most complicated, 4 minus 2 is less than 1 plus 2. So we started with the 4 and the 1, taken away 2 from this one and added it to the other side, and we've got 4 minus 2 is less than 1 plus 2. Okay, so let's just focus on the most complicated one. Hands up if you think that inequality has been observed, and you can only pick one, being done by lions. Okay, got one. Chicks, got one from Jada, another few, and chimpanzees. Lots of chimpanzees. It's actually the 3-day-old chicks. They are shown 4 items going behind. I mean, this is the sort of thing where I could probably save some time, but anyway. They're shown, they've got things that they like, and they're being blocked off by these doors, and they are shown 4 things going behind this one, 1 thing going behind this one, and then they're shown 2 things being moved from here to here. And when they're released from their little pen, they run round to this door. So they know that 1 plus 2 is bigger than 4 minus 2. And then the other 2, lionesses are the most basic one. They just tell whether one pride is bigger than their pride or not, so should they compete. And the chimpanzees do the addition. They have 2 sets of 2 bowls of chocolates, and one of them has got 4 and 5 in it, and one of them's got 1 and 7, and they pick the one that's got 4 and 5, because there are more chocolates. So it's a natural ability, but we have developed it to an incredibly abstract level and taken it away from any sort of real world. And obviously we still use it in the real world applications, but a lot of advanced maths is not related to fruits on trees or number of competitors in a group. And I think there's a comparison there to language. All of these animals are able to communicate within their own species. But as far as we're aware, and I might be corrected on this, humans are the only species who can talk about things that don't exist and can make things up. And so a natural question to ask is the nonsense that we're talking in maths any more meaningful than the nonsense of the Jabberwocky? They're both, we've developed a natural ability and we've maybe taken it too far. So that's our question. And if we are going to say yes, we are more, maths is more meaningful, then we need a good justification for it. And the approach that is taken by mathematicians is called the axiomatic method, and Euclid is the best example of this, one of the earliest examples. With the axiomatic method, you take a set of truths that you feel to be self-evident, and then you use logical deductions to produce new theorems. And so these are Euclid's axioms. Given 2 points, there is a straight line that joins them. There's a single straight line that joins them, provided they're not the same point. A straight line segment can be prolonged indefinitely, so you can just stretch it as far as you like. All right angles are equals, the whole is greater than a part, and so on. I think we can agree these are all fairly obvious facts. And from these 10 axioms, he produced 13 books of theorems, and it's one of the sort of most complete examples of the axiomatic method, certainly one of the earliest. But there is an issue with this approach to maths. For one thing, how do we know that 10 is enough? There might be geometry problems that we can't solve because we didn't have the 11th axiom that we're missing. On the other hand, what if we've got too many, and actually 4 and 8 contradict one another once you do enough maths? So you keep on producing theorems. What if eventually you can't actually have these 2 axioms together because they're actually contradictory? And there's no way, just by looking at the axioms like this, that we can tell. So this introduces 2 ideas. We've got consistency and completeness. A system is consistent if it never proves and disproves the same theorem. A fairly sort of natural way of defining consistency. And it is complete if every statement that can be expressed by the system, or every problem that can be expressed by the system, is either proved or disproved. And in incomplete systems, there are undecidable statements that you just have no hope of proving without introducing some new axioms. So this is Hilbert. He's another mathematician. He's got a nice hat. He, in the 1900s, wanted to prove that maths, or at least arithmetic, was both consistent and complete. And his hope, the ability that, the method he hoped to do this with, or the approach he hoped to take, was producing this approach to maths called formalist mathematics, where rather than thinking about the meaning behind the maths, rather than actually worrying about what those axioms mean, we just treat them as a list of symbols which we're allowed to manipulate in certain ways, and then if you just manipulate all of the symbols and produce all of the theorems, are there any contradictions? Is it complete? But we're not worried about meaning. We're not worried about whether it's true or whether it's false or anything like that. We're just manipulating symbols. So an example of this, we're all familiar with commutativity, maybe not with that word, but 2 plus 3 is the same as what? 3, lots of other things. It's equal to loads of things. 2 plus 3 is equal to 3 plus 2. It doesn't matter which way around you do it. And so that actually is taken as an axiom, it's not a theorem. And in our symbols language, we're going to write it like this. So for any x and any x star, if we do x plus x star is equal to x star plus x. That's an axiom. And then one of the things that we're allowed to do to prove things is to take a special case. So if I wanted to prove that 1 plus 2 equals 2 plus 1, it's a very simple proof. I say, this is an axiom that says that it's true for any numbers, and so it is true for 2 and 1. And that's my proof, that 1 plus 2 equals 2 plus 1. Okay, so if we do that, can we prove that maths is complete and consistent? This is another mathematician, Gödel, and he's the focus of the talk, really. He came along 11 years after Hilbert sort of suggested this program and said, no, it's impossible. If maths is consistent, then it must be incomplete. There must be problems that you can't solve. And if there aren't problems you can't solve, then maths is inconsistent, which is even worse. And he also showed that there's no hope of proving that a system is consistent using the system itself. So we can't use maths to prove that maths is consistent. That might be a more sort of obvious idea to you, that you can't sort of prove yourself consistent. So an outline of the theorem is what I'm going to give. The sort of core concept behind it is sort of the liar's paradox that you might be familiar with. This statement is not true. This statement is not true, can't be true or false, because if it's false, then it is not true, and so it's true, and if it's true, then it's false, and so there's a contradiction. It's going to be a little bit more complicated than that, and just make sure I've got my references all done correctly. This is the main book that I will be basing this on, so it's not actually Gödel's own symbols or terminology, it's Hofstadter's, and this is a really interesting book. It's very big, but it's really interesting, and it intertwines Gödel's ideas with the art of Escher, those paintings that sort of draw themselves, and the music of Bach, where there's a lot of self-reference as well. So it's a really interesting book if you've got time to read it. But obviously this 30-minute talk will cover absolutely everything in there, and you won't need to. So the issue with doing this in maths is that English is very good at describing English. English has got words, and so it can talk about itself really easily. But maths is to do with numbers, and so maths doesn't talk very easily about maths itself. It just talks about numbers. So how are we going to use maths to say this statement is not true? So Gödel's approach is called Gödel numbering, and it's as simple as assigning a number to each of our symbols in our logic statement. So some of these symbols won't be familiar, but the basic idea is for each statement, we assign it a number, and so the theorem or the formula is just a number, and we can do proofs as well by separating each formula by 2 zeros. So a proof also has a Gödel number. So every statement in maths, or at least in this formalist approach to maths, is equivalent to a number, and that number is just equivalent to the formula. One thing to just talk about is this successor function here. If we want to give a Gödel number for this last line of this proof, we don't want to have a separate number for 1, 2, 3, 4, 5, 6, 7, 8, because then we need infinitely many different codings. So what we do instead, and this is just for arithmetic, so whole numbers, natural numbers, it can be extended further, but we're simplifying things. We say that 0 is 0, that makes sense. 1 is the successor of 0, it's the number that comes after 0. And 2 is the successor of the successor of 0, and so on, and so forth. Does that make sense? Yeah. So it just, so technically, if I want to make this proof proper, I need to say s of 0 plus ss of 0 is equal to ss of 0 plus s of 0. So 1 plus 2 equals 2 plus 1. And now because we've done that, we can number these theorems. So commutativity is this, as I've written on the board, and the Gödel number is that. It's a very long number, but it exists, and we can talk about it. And I'm going to use this convention where capital letters are the formulae, so they're like the logic symbols in the formulae, and lowercase letters are the Gödel numbers that correspond to them. Okay, so here's the proof. Got the first line and then the second line, and the Gödel number of the proof is even longer because we need to put them together with a 0, 0 in between, but it's still just a number. Okay. So, in order to get to the Gödel statement that is unprovable, we need two concepts, two formulae. One of them is the PP formula. This takes two variables, x and y, and it says that x is the Gödel number of a proof of the formula with Gödel number y, or just in terms of capital letters, x is a proof of y. So it just says, we can prove y, and one of the ways that we can prove it is using the formula x. And so x will be a sequence of steps resulting in our theorem y. So in terms of the previous slide, this thing is true because the red number is the Gödel number of the proof, and the blue number is the Gödel number of the theorem 1 plus 2 equals 2 plus 1. So this statement is true. And it's a little bit hazy at this level of depth, but because we are just assuming we can enumerate all of the theorems like a computer could do it, we don't need to have any understanding ourselves, then this is just a thing that can be checked. And so it is just a relationship between two numbers. There's not any meaning to it. I've sort of talked through that. So that's the proof, and that's the theorem. And then we've got, this is the terminology of Douglas Hofstadter, not Gödel, arithmetic unification, which is where you take a Gödel, you take a formula, and you plug into any variables in that formula the Gödel number for f. So you make it talk about itself, but in number form. So you take some formula, and AQ just means that y is the arithmetic unification of the formula x. So here's an example. X plus 0 equals x. Does everybody agree? Yeah. That's got Gödel number this. So if we want to arithmequine it, we have to plug the number a into both cases of x. And when we plug it in, we need to use those s's instead of the actual number. So this is the arithmetic unification of a. Okay, and so that means there are a s's. A is a massive number. Each s is represented by 1, 2, 3. So the Gödel number here is going to be millions of digits long, but it exists, and we could write it down if we wanted to, but I don't want to. And b is the arithmetic unification of a, so AQ, AB is true. That's just a way of talking about arithmetic unification. So now we get on to Gödel's formula. We're doing okay. Gödel's formula is this, which is looks quite complicated, but what it essentially says, I mean, if I were to read it, it would say it's not true that there exists an x and there exists a y, such that the proof of y is x and the arithmetic unification of z is y. But that basically means z is a formula whose arithmetic unification is unprovable. So this sentence is really important. So that's f. And it's only got one variable, z, because once we actually interpret it, it's just talking about z. X and y are sort of taken up by these exists. So it's got one variable, z, and it says z is a formula whose arithmetic unification is unprovable. Okay. Then we get Gödel's formula G, which is the arithmetic unification of f. So we take this formula and we plug in our Gödel number f, and we get this sentence. And what does G say? Well, G says that the arithmetic unification of f is unprovable, because f was the arithmetic unification of z is unprovable, and we plugged in f to z. Is everyone happy with that? So we get the arithmetic unification of f is unprovable. But what is the arithmetic unification of f? Is anybody email me? Yeah? Is that?
It says G on the
Good spot. I'm glad somebody's awake. Yeah, G is the arithmetic unification of f. That's how we defined it. G is the arithmetic unification of f. So G actually states that G is not provable. And that's where we get our this statement is a lie. So if we prove G, then it's a contradiction, because we've proved that something that itself is unprovable. And if we disprove it, then in order to disprove that it's not provable, you need to prove that it is provable. And so we have a proof for G, and we also have a disproof for G, and so our system is inconsistent. So actually, it looks like these are the same thing, but technically if we prove it, it's a contradiction, and if we disprove it, then it's an inconsistency. They're subtly different things, but the important thing is G can neither be proved nor disproved. So it's an undecidable statement. Okay. Right. So that's his first theorem. His second theorem is that no system can prove itself consistent, and this goes off the previous slide. So we said if our system is consistent, then G is not provable. So if you prove that it's consistent, then you've proved that G is not provable, which is proving G, which is a contradiction. So if you can prove that you're consistent, then you prove G and you disprove G, and you get a contradiction. So no consistent system can prove its own consistency. Okay, I realise that's quite heavy. He was not that impressed, but I guess the question is, G is a contrived statement that we've designed with the intention of being undecidable. So do we care that we can't prove it? Is it actually of any interest to us mathematically? Well, I guess a different question is, are there any questions that we can't prove that matter to people? And the answer is yes. So this is Cantor, another mathematician, and he had ideas about the infinite. Specifically, one of the things he showed was that the real numbers, like pi, e, 1, 1.8, minus 12, they are more numerous. Oh dear. they are more numerous than the whole numbers 1, 2, 3, 4, which seems kind of straightforward, but actually it's a lot less obvious than you think. And for his ideas of the infinite, his ideas were called the grave disease infecting mathematics. He was called a scientific charlatan and even a corrupter of youth. So not very nice. But Cantor said, is there an infinite number between this set and this set? Is there an infinity between these two? That's called the continuum hypothesis. He spent the end of his life trying to prove it, and about 20 years later, Gödel showed that you can't disprove it, and then 20 years after that, another mathematician showed that you can't prove it, and so actually it's a problem that can't be proved, and he wasted many years of his life, and died in a sanatorium, unfortunately. That's very sad. Gödel, anyway, he dies horribly as well, unfortunately. Another example that is closer to home is Euclid's axioms. When I showed you to them, I said, oh, they're already obvious. Is there one that jumps out as maybe less obvious than the others? Show me on your hands. I've seen maybe one or two. Number 5, because if you read the others, they kind of make sense. If equals are added to equals, the wholes are equals. If we read number 5, if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, blah, blah, blah. What it's saying is actually this. If alpha and beta add up to less than 180 degrees, so they're not both 90 degrees or more, then these lines must meet, and they meet on that side. And mathematicians spent 2,000 years trying to prove this, trying to prove number 5 from the others so that we didn't need to assume it. And the people who tried include Ptolemy, whose maps were used by Christopher Columbus, Proclus, Ibn al-Haytham, who first explained how vision works by light bouncing off the eye. This is Omar Khayyam, who wrote the Rubaiyat. They all tried to prove it and actually produced proofs that turned out later to be false. And the reason for that, and in fact there's an Italian mathematician who said the hypothesis of it not being true is absolutely false because it is repugnant to the nature of straight lines, but that's not a proof. So the reason why you can't prove it is if you don't assume it and you assume different things, then you actually get perfectly valid geometries. So one of the things that you can deduce from that 5th axiom is that the sum of the angles in a triangle is 180, and we tell you that regularly. But actually, if you're working on a sphere, then the angles in a triangle add up to more than 180. And if you're working on a saddle, I don't know why, then the angles in a triangle add up to less than 180. And these are two very valid geometries, and that's because the 5th axiom is an undecidable statement. And I mean, this is geometry on the Earth, so obviously it's really important that we can do that. And like Einstein's general relativity relies heavily on non-Euclidean geometry, so it's actually a really important theory. Okay, so I said in the title of my talk that it doesn't keep me up at night. So why is that? Because surely we've shown that mathematics, first of all, there are problems that we can never solve, and we could spend all of our lives trying to solve them and never get anywhere. It's pretty sad. and also we don't know where the maths might be inconsistent. So in terms of the inconsistency, it's maybe not a very sophisticated reason why it doesn't keep me up at night, but I just feel like maths is consistent. I believe the axioms, planes still fly, iPads still work, everything that we've done with maths works, and if there is an inconsistency, we won't need to throw everything out. It will actually just create a new era of maths where we study what theorems we can keep, what theorems we need to throw away, and it will actually be fascinating. I don't believe it will happen, but if it were to, I wouldn't mind. And then in terms of incompleteness, I think rather than seeing an undecidable statement as a dead end in your exploration of maths, you should see it as a crossroads, lovely represented by these crossroads here, where, like with the Euclid axiom, if you choose different assumptions, you get completely different, interesting mathematics. So instead of having a single universe of maths, you have a potentially infinite number of beautiful universes to be explored. Thank you very much. Does anyone have, like, 2 questions? 2 minutes of questions? Nothing too hard, please. No? Yes?
How does what you just talked about link into Escher and that?
So it's really to do with the self-reference. I did want to bring along the book, actually, but I forgot this morning. He interleaves each chapter about maths with like a chapter about art and then a chapter about music, and it's really that thing about how can you make a system refer to itself. And Escher does it by sort of drawing arms that paint themselves, and Bach does it by having themes throughout his music that are referred back to constantly, and things like the fugue, which one voice plays it one way up and the other voice plays it the other way up, and they happen to work as a piece of music. It's just sort of like neat tricks like that, basically. I don't think it's like a solid link, but it makes for a nice book. So. Any other questions? No? Okay, thank you very much.